In this video, we're going to be talking about the molecular orbital theory. In the last video, we talked about hybridization. So in hybridization, we talked about how the electrons or the orbitals are overlapping each other. In this particular case, we're in molecular orbital theory, we're going to be talking about how the electrons throughout the entire molecule are arranged. So who's to say that there's only two electrons that get shared in between two orbitals? Why can't all the electrons be at play here? What makes that difference between hybridization and the molecular orbital theories? So now, just a little recap. Hybridization is the rearrangement of electrons in available subshell orbitals to allow for maximum bonding. So the types of orbitals, you have your S subshell. All right, S subshells are spherical in shape. You have your P subshell. This all goes back to quantum mechanics. And the P subshell has that dumbbell shape. So when we talked about sigma and pi in the past video, remember that sigma is a direct overlapping of the orbitals. It's a direct overlapping of the orbitals, and then you have the pi bond. The pi bonds are delocalized, meaning that they are found above and below. So if you watched that video, you saw that they were above and below, or they were front, forward to backward. So these are your pi bonds here. So we're going to still be using sigma and pi bonds in reference to the molecular orbital theory. Now, when we talked about in hybridization, single, double, and triple, we saw how the pi bonds are arranged in the double and triple. So we can count the number of sigma and pi bonds in relation to the type of bond that you're working with. So in a single bond, you have 1 sigma, 0 pi. For a double, you have 1 sigma and 1 pi. For triple, you have 1 sigma and 2 pi's. Notice that all of the different types of bonds have sigma bonds, but not everything has a pi bond. And so as you add in those extra bonds, you also add in the extra pi bonds. So what we're going to be looking at now is atomic versus molecular orbitals. So that was atomic there. So molecular orbital theory, I'm just going to abbreviate it, MO, describes the distribution of electrons throughout the molecule, not just around the individual atoms. It also describes the energy of the different electrons. Now the energy is based off of quantum mechanics. It's the shape of the orbital. We kind of talked about this a second ago, the shape being spherical, it's being the dumbbell, or if you're a D shell, you have that weird, the dogwood flower shape. If you have the F orbitals, you have 4 on top and 4 on the bottom. But we're not going to be looking at the D or the F because we're only focused on the S and the P. So it's the shape of the orbitals. And it's the fact that the electrons may move around the entire molecule. So, just like we saw with the orbitals before, the maximum number of electrons you can have per orbital are 2. The type of orbitals that we're going to have, so there's 2 different types of orbitals. There are sigma and pi orbitals. So as we talk about the different types of orbitals, we can expand on that, and we can talk about bonding versus anti-bonding. Bonding versus anti-bonding. All right, so bonding orbitals are where the electrons are generally found between the nuclei. Just like we saw in hybridization, the electrons are in between the 2 nucleus of the atoms. They are attracted by both nuclei, which results in a lower state of energy. If you have a lower state of energy, you are going to be more stable. So the molecule will be able to exist longer periods of time and not fall apart. So the less stable, the less likely that molecule will form in nature. Now, anti-bonding happens to be with your sigma S, and we'll explain this in just a few minutes here, sigma P and pi P. And all these have stars on top. When we start to look at the orbital diagrams in just a couple minutes, we'll see that we have these little stars up on top right hand side. These stars represent anti-bonding orbitals. Anti-bonding orbitals really means the electrons that are found outside of the centers of the nucleus and in between the 2 nuclei. So what we're doing here is we'll be looking at bonding electrons versus anti-bonding electrons. And what those do is they help us to determine the bond order. All right, the bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. And we divide it by 2 because how many electrons are per orbital? 2. So we need to take out that factor 2. All right, so we divide this by 2 because of the fact that we have 2 electrons per orbital. So let's look at an example, and we're going to focus on the element hydrogen and hydrogen gas. So make sure you have this equation out as we do this. So hydrogen has 2 electrons. The orbital diagram that you see with hydrogen is sigma 1s and sigma star 1s. Sigma star has 2 orbitals there. So just like we saw in electron configurations, you're going to count the number of electrons and you're going to fill it in from the bottom up. And so that's what's really going to dictate the bond order. So in this case, we have 2 electrons and they fill in the bottom orbital. Now, once we calculate the bond order here, the bond order is going to be, so remember this star up here represents anti, so this one is your bonding. So you have 2 minus 0 divided by 2, which gives me a bond order of 1. Now this is just an example for a neutral molecule of hydrogen. So if we take H2 with a minus 1, Now we have 3 electrons. So we're going to take the same diagram here, and we're going to fill this in, and we're going to see how it affects the bond order. So we have 1, 2, 3. It doesn't matter which side you put that in, as long as you count it. So the bond order now is 2 minus 1 divided by 2, which gives me 1/2. So what we learned from this is that the bond order for hydrogen neutral molecule is 1, and the bond order for the second one is 1/2. The higher the bond order, the more stable the molecule is. It also reflects on the bond length. So the higher the bond order, more stable and shorter bond length. So as this number gets higher and higher, the molecule will become more stable. And we see that as we go higher in the number of electrons. So we're going to be looking at the same type of example, but we're going to be looking at oxygen gas. Oxygen gas has several more electrons than hydrogen, and has its own diagram. These diagrams you do not have to worry about memorizing. You can look these diagrams up either in the textbook or online. So the diagram that would be for oxygen, so this is just oxygen gas, and one other detail is that we've always been looking at the valence electrons when we talked about hybridization and Lewis structures. Molecular orbital theory, remember, it reflects all of the electrons. So you have to count both core and valence. So look at the atomic number for oxygen. It's 8. It means you have 16 electrons. The diagram for oxygen would be, so we're going to look at oxygen gas now. And oxygen gas has 16 electrons total. We focus on the atomic number, not the valence electrons here. So each oxygen has 8 electrons, and 8 times 2 gives you 16. This would be the diagram for oxygen gas. These diagrams are going to be different for different molecules. They're not always going to be the same. So, and that's why you have to look these up. I'll throw a picture up right now that shows you some different examples from our textbook that we use. And so how do we go about filling this diagram in? Well, it's simple. We start off with knowing how many electrons we have, and then we go from the bottom and work our way up. Now, if you remember back doing electron configurations, once we get into these that have 2 orbitals beside each other, you fill in 1 at a time, and then you double up based off 100, and then you go up and do the same with the second. And these only show up in the pi bonds specifically. So in this case here, we're going to be doing 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's our diagram. Now what we're going to use the diagram for is to figure out the bond order for this molecule. So remember the stars represent the anti-bonding. So we're going to count the bonding orbitals first. So we have 2, 4, 6, 8, 10, minus 2, 4, 6, because you have 2 up there, divide by 2. So 10 minus 6 is 4, 4 by 2 is 2. Now if you saw in the first example, hydrogen gas bond order was 1, the bond order for oxygen is 2, so that means the oxygen gas would be more stable because it has a higher bond order. It also means that you're going to have a shorter bond length. So one of the things that you should remember back to bonding is that double bonds have a shorter bond length than single bonds, and triple bonds are going to have shorter bond lengths than the other 2. And so the shorter the bond length, the more stable that molecule is. It's going to take more energy to break it down. So what happens if we are to change the oxygen and we take away an electron? how would that affect the diagram here? Well, what would happen here is in this diagram, you would lose an electron. So instead of it having 16, it would have 15 electrons. So this would be the diagram for O2 with a +1 charge. How would that affect this bond order? So now the one to take away is the pi bond, the antibonding. So it would be 10 minus 5 divided by 2, which gives me 2.5. And so you can see by taking away that electron, the bond orders increase. Now keep in mind what electrons do. They repel each other. So if you take away an electron, most likely you're going to stabilize that molecule just a little bit more. So let's take the third option and let's add in an electron here. So this would be 17 electrons. So that means you're still going to have this one up here, and we're going to add in an electron here. So now we see that there's a little difference here. So we have one more electron as the antibonding electron. So 10 minus 7 is what? 3. 3 divided by 2 gives me 1.5. So we can see by adding that electron in, that extra electron, now it's caused our bond order to go down. So as our bond orders decreased, that means this molecule is the least stable, this molecule is the most stable, and this molecule is just neutral. So what's the importance of this? This diagram helps to illustrate how the electrons are arranged throughout the molecule. From this diagram, we're able to figure out the bond order of that molecule. Now there's one last detail we want to make sure we understand, and that is magnetism. All right? There's two different types of magnetism. There's paramagnetism and there's diamagnetism. And these magnetisms are determined by the electron's configuration, how they're oriented in these orbitals. So you have diamagnetic, and then you have paramagnetic. So when you have diamagnetism, you're going to have orbitals that look like this. So there's not going to be any singles in here. When you have paramagnetic, you're going to have just a single electron in an orbital. And all it takes is one orbital to have that configuration to be paramagnetic. Think about a paratrooper. When you're a paratrooper, only one person jumps out of the plane at the same at any point in time. They all jump out just a single. So think about para being a single. So when we look at the diagram that we have drawn here, this is for O2 with -1 charge. What type of magnetism would this be? Well, it has a single electron up here. So we would say that O2 -1 would be paramagnetic. The same would be true for that of the O2 with a neutral charge. If we take away an electron, it's also going to be paramagnetic. Now, if we go back and look at the hydrogen, right, it had a configuration. So in this case, it had 2 electrons. It had 2 on the bottom. Well, hydrogen would be diamagnetic. So what exactly does this mean? Think about iron and think about aluminum. Iron, if you take a magnet, it sticks to it. You can pick up any steel that has iron in it because it's magnetic. However, if you take a magnet and you put it next to a piece of aluminum, it's not going to be magnet. It's not going to pick it up. So when we talk about iron, it's magnetism. Iron would be paramagnetic and aluminum would be diamagnetic, because what happens is the electrons are trying to go towards the magnetic field, which is the north and south poles. They're trying to align themselves, but they can't. So aluminum will not be magnetic. However, iron's electrons are arranged in a paramagnetic configuration, and so when you hold a magnet to it, the electrons align themselves to wherever the pole, north and south poles are on the magnet. So what do we get from molecular orbital theory? We get this diagram. We understand how the electrons are configured throughout the entire molecule. we can determine the bond order from that diagram, and then we also can determine the magnetism from the diagram itself. Thanks.